And let me go ahead and pull up Chapter 10, Goal 3 with my screen share. See if my internet is going to, oh, it looks like it's going to work this time. There we go. Okay, I'm going to move my video over here. There we go. All right. So got 14 of us here in the participants. Chat's open, and we're going to take the last thing with amines. So what I'm hoping to do now is show you, we don't have very many reactions on amines, which is why I don't have very much homework yet, which is what we're going to work on. But the key things that it does is we're looking at it as a Lewis base and or a nucleophile. Those are the two things we're going to talk about most here. So our goal are the reactions. Again, that lone pair plays a big role in all the reactions we do. So the first thing we need to think about is that all amines, whether or not they are soluble in water, will react with strong acids to make quaternary ammonium salts, okay? So in this case here, we have, let me go to red. We have an aliphatic amine because there's a CH2 group in between that and this benzene over here. So we have an aliphatic amine, but it reacts with strong acids like HCl, HBr, sulfuric, etc., to create these charged nitrogen species here. It's basically using the electrons from the lone pair to make that new bond with the hydrogen here and giving us a counter ion to go with it. So this happens. And when they do form these quaternary ammonium salts, almost all of them are water soluble, okay? So we have several different things that we use as pharmaceuticals that are poorly soluble in water. It makes it very difficult for us to ingest. However, if you make them into salts, they tend to be water soluble. So what you'll see a lot of, if you look at your prescription bottles, it'll say something like bisulfate or sulfate or whatever. And so the most classical example is actually cocaine, because cocaine, when it's snorted as a powder, it actually is the sulfate salt, the hydrogen sulfate salt. However, if you take that salt away and make it water insoluble, that turns it into crack. And that is sublimable and water insoluble. So don't do that, but that's why it works. Crack and cocaine are the same thing. They just happen to be different. One's a salt and one's not a salt. Okay, so that being said, how do we make these? Okay, so what we learned from the last chapter is that we can nitrate a benzene ring using a nitric acid plus sulfuric acid to generate that positive charge on nitrogen. And when we have that, we can then reduce that down to make it into an aromatic amine, okay? So it's very difficult. There's very few reactions where you can actually use the nitrogen, the amine as itself to attack, okay? And this is because we're looking at electrophilic attack, and the nitrogen already has electrons on it, so we don't see that reaction very much. We actually use the nitro group as an electropositive group, that positive charge, and to nitrate, and then we do a reduction. In this case right here, we're using hydrogen and nickel, and what that ends up doing is reducing off both of these oxygens, turning them into water, and then the last equivalent of hydrogen actually ends up reducing the nitrogen all the way down to that. So this is how we make aromatic amines, okay? But let's talk about making aliphatic amines, okay? So one of the reactions we learned with alkyl halides is that an amine will react with an alkyl halide to form our new covalent bond, okay? And so this is just the first step of the reaction. And then when we lose this hydrogen to a Lewis base, we end up regenerating a new amine species, okay? So this works out okay, except for the fact it's hard to control. Because once you've done this reaction and you lose this nitrogen, you gain, lose the hydrogen to your Lewis base here, you regain your lone pair on the amine. when you regain that lone pair on the amine, it can now act as a nucleophile again. So what we see here is that the first reaction forms that to give us our salt here, and then some other species here can act as the base, which will regenerate our amine, in this case a secondary amine. So notice this only has one R group on it here. So we took it from the previous page. This has one R group on it. We've added a second R group by doing this first step right here. Now, once we generate that, we can either have reaction by the primary amine, the only one R group, or we can have reaction by the secondary amine. And there's no difference in reactivity. The lone pair is the part that gives it its reactivity. So what that means is that now that we have a new secondary amine, it acts as just as much of a nucleophile as the primary amine, and our secondary amine will then react again. So this is very difficult to control, and so it's very difficult to make aliphatic amines that are just monosubstituted or disubstituted. You typically go again and again and again till you end up with the trisubstituted or even the tetra ammonium salt, the tetraalkyl ammonium salt. So we actually have a strategy for getting around that, but we don't learn that in this particular reaction. But so to make an aromatic amine, we nitrate and then reduce it down to the amine. To make an aliphatic amine, we have to be very, very careful or do other chemistry. But again, the whole point is our amines are all nucleophilic and will react again and again and again. All right, so those are the only reactions we have in this amine section. So what I want to do is spend the last 30 minutes or so talking about our first part of spectroscopy, which is the IR spectroscopy. So what I want to talk about is three things related to IR spectroscopy, and it's basically kind of what it is, and then what we really, really need to look for, and then some common themes we'll see throughout our IR spectroscopy. What I like to do is I like to actually use IR spectroscopy to prove to you that these functional groups actually exist, prove to you these bonds actually exist, and that's why IR spectroscopy is so powerful. And it should, once you start thinking of it as, oh, it's actually measuring the frequency of two atoms, and that frequency correlates exactly to those two atoms, then you'll start to see that IR spectroscopy is a fundamental proof that you've actually made these bonds, okay? So the first thing is that when we talk about IR, it's part of the electromagnetic spectrum. Basically, all visible light is what we see. Those are light that has an electronic component and a magnetic component and a direction component. And we see a small amount of that. And then outside of that band, there are other bands we can use, okay? So when we talk about spectroscopy, we're typically talking about wavelength, and we do it in a specific way called wave number. So wave number, which is a CM-1 or per centimeter, is the number we are going to pay most attention to, okay? So if we look at the entire magnetic spectrum here, we have everything from gamma rays way over here, which are very, very short wavelengths. And then we have X-rays, which are not as short, UV, and then we get into the visible here. And notice that wavelengths are getting longer and longer as we go in this direction here. So these are longer wavelengths, okay? And therefore they react, they are absorbed by the molecules in different ways, okay? So once we get out of visible, we get into the IR, infrared, and then we have microwaves and all these other longer radio waves. Some of these waves can be miles long. They're way down at that end of the spectrum, okay? So what we're looking at is the ones right here. And the ones right here happen to be right in a frequency where it's approximating the frequency of that actual bond length, or that it's that distance of that bond length, okay? So if you have a wave that's has the same length as the atom, the length of the atoms, and the energy of that atom to atom bond, that's where we're looking at when we look at infrared spectrum, okay? So in general, we call this infrared region between this wavelength and this wavelength here. But because it's really hard to use that number of 2.5 times 10 to the minus 6 meters, we've actually made it simpler, okay? And what we've done is we've expressed it as reciprocal centimeters, or number of waves per centimeter. And that takes it down to two numbers that are much easier to remember. Those two numbers are 4,000 reciprocal centimeters, or wave numbers, to 400 reciprocal wave numbers, okay? So what that means is that these are actually longer and these are shorter, but what we'll end up with is that's the range we're going to look for. The high end, our left side of our spectrum, is always going to be this 400 wave numbers, so 4,000 wave numbers, sorry. Our right end of the spectrum is always going to be this 400 wave numbers, okay? Now, when we look at that, I want you to pay attention to the fact that we have 4 bands that we really need to pay attention to, okay? And these are the 4 bands. This is not in the book, okay? If you print out one page from my slides, print out this slide, okay? Because this will kind of help solidify the whole concept of IR, okay? So let's go back to talk about those wave numbers again. So here's our 4,000 wave number band. Here's our 400 wave number band, okay? Within that, we have 3 other divisions that I want to talk about, which divides us into 4 zones, okay? We have the first zone, and in this first zone, we have what I like to call the heavy atom, light atom, high frequency, okay? So think about it. In that band, you have carbon, oxygen, or nitrogen bonded to a hydrogen, okay? So we are looking at a frequency between carbon and hydrogen. We're looking at a frequency between oxygen and hydrogen, and nitrogen and hydrogen, okay? So anything that has a heavy atom, light atom, will vibrate in the range between 2,500 and 4,000 wave numbers, okay? And you think about that, think about those 2 different atoms on a spring, okay? The carbon atom is the heavier of the 2 atoms. The hydrogen's the lighter of the 2 atoms. And so that hydrogen is springing back and forth very rapidly, okay? Higher frequency. And because it's at higher frequency, it has a lot of energy in it because it can move very rapidly, okay? So everything in that band from 2,500 to 4,000 is some kind of atom bonded to hydrogen, okay? Now, the next band over is we're going to look at, we start looking at, these are a big atom to big atom vibrations, okay? So the first thing we have here is our triple bonds, okay? So now you have a carbon bonded to a carbon 3 times, okay? So you have a sigma bond, you have a pi bond, and another pi bond, okay? So now these 2 atoms are very close together, and they're very tightly bound. They have 3 different bonds holding it together. So imagine that they are so tightly bound that to make that bond vibrate will take a lot of energy, okay? It's not going to it's not going to move very much, but you have to add a lot of energy to get to that. So think stronger bonds, higher frequency, okay? So in this band, between 2,500 and 2,000 wave numbers, right here, this is what we call our triple bond band, okay? Only triple bonds will show up here. Every once in a while, you'll see a hydrogen if it's bonded to sulfur. But don't worry about that in this class. But every once in a while, you will see that. Okay, so now we have big atom, small atom, giving us bonds to hydrogen, very, very high energy, very, very high frequency. Now you have two really tightly bound atoms, and that's a slightly less frequency, but a very strong bond, okay? So now the next thing down would have to be double bonds. So a carbon-carbon double bond, a carbon-oxygen double bond, or a carbon-nitrogen double bond. They're not triple bonded like the ones here, and they're not single bonded like the ones on the other side. So this is our double bond band. And this is between 1500 and 2000 wave numbers. And you can think about it as, okay, it's not as tightly bound as the carbon-carbon triple bond, but it's more tightly bound than the carbon-carbon double bond. Therefore, it's going to be right in the middle, okay? So that gives rise to our double bonds. And then this last zone, everything 15 and below is what we call the single bond range. This is where carbon halogens show up. All of our carbon-carbon bonds are there, just single bonds. Our alcohol single bonds are there, etc. So if we look at these bands as a function of how tightly those atoms are bound or how strong that bond is, you will see that this band is always with hydrogens. This band is triple bonds, double bonds, and single bonds. It makes order to our system. Now, as we go through our functional groups, we're going to see them show up in these different regions, okay? So we have 20 minutes left. So let's go through some functional groups here. Okay, so if we're thinking about this compound and we look at the different functional groups we have here, and what I'm talking about by functional groups is we don't have to name them just yet. We will name them all by the end of the semester, but let's look at this. This right here is actually a, if we turn that into a carboxylic acid, so we have carbon-carbon double bonds, we have a carbon-oxygen double bond, we have a carbon-oxygen double bond, we have CH bonds here, we have hydrogens here too. So we should see some bonds up in that 4,000 to 2,500 range from all of these ones in red. I'm going to change colors to green. So in the green, we have these carbon-carbon double bonds, carbon-oxygen double bonds right here, okay? And if we change again to blue, we have a carbon-oxygen single bond, a carbon-oxygen single bond, a carbon-carbon single bond. Let's see, we have a carbon-carbon single bond. So we should see something in that band as well. Let's see, I didn't identify this. This is going to be up in that high zone, that 2,500 to 4,000 range. The blue ones are going to be in that 1,500 and below range. And the green ones, because of the double bonds, are going to be between 2,500 to 2,000 is our triple bonds. We don't have any triple bonds, so we're not going to see that. So let's take that out. So the stuff in the green band is actually going to be from approximately 2,000 to 1,500. 2,000 to 1,500 are going to be that green. So let's look for those bands in our spectrum here, okay? So if we look for those bands in our spectrum, the first thing we want to look at is where are our wave numbers, okay? So let's look at our wave numbers. Our wave numbers, this is 4,000 right here, and this is 2,500 right here. Okay, this is 4,000 to 2,500, so that's what our high band is. This is where all our carbon hydrogens should be. This is where all our oxygens hydrogens should be. Let's see that the next band goes down to about 2,000. So this band here is our C triple bond band. The 2,000 to 1,500, this is our C double bond, C double bond O band. And then this is our carbon, oxygen, carbon, carbon, and we didn't have any nitrogen, so there. So let's look for bands that we're going to see. So we know we're going to see something in the high end because we have those hydrogens there. We have CH hydrogens, both aromatic and aliphatic, and we have an OH hydrogen. So we see those here in this band right here. This is the OH and the CH bonds right here. We don't have any triple bonds, so this band is pretty much empty. But now we do have carbon-carbon bonds and we double bonds, and we have carbon-oxygen double bonds. And so we actually see different peaks for each of those different types of carbon-carbon double bonds and carbon-oxygen double bonds. And then all of these peaks can correlate to the carbon single bonds, the carbon-oxygen bonds, all of those other bonds here. So we have lots of those. So we have lots of peaks available to us. So by looking at the different energy bands, we can start to predict where we should see things and where we shouldn't see things. So let's use this same strategy for different functional groups, okay? So what we'll see here is this is a correlation to that exact same thing I was talking about before. The only thing we're doing different here is we're adding whether or not the intensity should be strong or the intensity should be weak. So things like oxygen, oxygen, hydrogen bonds, and amine bonds, these are going to be strong because we're going to see them, they're going to be very strong. As we go to triple bonds, they're going to get weaker. And as we get to double carbon-carbon double bonds, they also get weaker. So we're just looking at the varying intensity for here. But what I want you to be able to do is pick out which bands these different groups are in, okay? So if we look at an alkane only has a carbon-carbon bond and a carbon-hydrogen bond. So we should only see things in two different regions. And we do. We see it in the 1500 to 4000 region, which is where our carbon-hydrogen bond is. And we see the 1500 right here and below here for the carbon-carbon bonds, okay? And notice we don't see anything in those other two bands. Those other two bands are right here in the middle. There's nothing in this band and there's nothing in this band because there's no functional group there, okay? So we only see the high band and the low band in alkanes. So if we convert our alkane to an alkene, should we see a different IR spectrum? I think we should, because by here we only had a carbon-carbon single bonds and a carbon-hydrogen single bonds. When we go to an alkene, we're now going to have a carbon-carbon double bond. So we're going to have a new band show up in our system. So when we go to an alkene, we now see something in that 1500 to 2000 band right here. We've added a functional group. So we've added something in that band that was not there before. Notice all the rest of this is just carbon-carbon single bonds and carbon-hydrogen. And so what we'll see is those show up down here. These are the carbon hydrogens. This is the carbon-carbon double bond, and this is all the other bonds, okay? So if we go from an alkene to an alkyne, we should see a new band in a new region, okay? So when we go from that alkene to that alkyne, we see that triple bond show up between 2000 and 2500. We have a functional group. And notice the one between 1500 and 2000 went away because we don't have any carbon-carbon double bonds anymore. We only have triple bonds. So we can actually watch it move from band to band to band, okay? Notice again, we still have our carbon-hydrogen stretch down here. And below 1500, we have all of our carbon-carbon stretches, single bond stretches. Okay, so let's see if we can find another functional group here. We went from an alkane that only had things in 2 bands to an alkene that had things in 3 bands to an alkyne that had things in 3 bands. So let's go to an alcohol. So By going to an alcohol, we have now changed from just having a carbon-hydrogen band to having a oxygen-hydrogen band, okay? Now, what do we know about oxygen and hydrogen here? Is it has a strong hydrogen bonder, okay? That's our strongest hydrogen bonding thing. So anything with an OH group is going to have a broad peak. Notice how big and wide this peak is here? It's still, 2,500 and above. It's still in our carbon, hydrogen, oxygen, hydrogen zone. However, it's big and broad, okay? So it has everything to do with the fact that it hydrogen bonds, okay? And notice we don't have any alkenes or alkynes, so we have nothing in this band here. This band is completely empty, and we only have carbon, oxygen, and carbon-carbon stretches below, okay? So by just looking at our different bands, we can identify functional groups for each and every one of our systems. Okay, so let's go to an ether, okay? When we go to an ether, we've taken that that oxygen, we went from an alcohol to an ether. And so from that, we've taken away that oxygen-hydrogen peak, okay? We no longer have that hydrogen bonding peak. And therefore, this big, huge dip we had up here goes away, but we still have carbon-hydrogen, so we still have something in that band. We have no double bonds, no triple bonds, so there's nothing here. But now we just have our carbon-oxygen stretch and our carbon-carbon stretch, single bond stretch. Okay, so what I think you should be able to look at is looking at those bands from here, looking for what's in those different zones. We should be able to pick out what bonds are available to us in those compounds. And then from that, we can also identify different functional groups. Okay, so now we've moved on to something with an amine. Okay, amines can have hydrogens on. If it's a primary or secondary amine, it will hydrogen bond, meaning we'll have something in this 2,500 to 4,000 range, only if it's a primary or secondary. If it's a tertiary, it has no hydrogen there to hydrogen bond, and therefore we don't see it in that band, okay? So the other cool thing is that primary amines, because they have two hydrogens, actually have two bands. Each of these hydrogens are different. They show up as two bands. So this is a primary amine because it has two small bands. If it only has one hydrogen on it, it'll only have one peak in that 2,500 to 4,000 range. And again, with no hydrogens, there's nothing there. Again, no double or triple bonds here, but we end up adding probably a carbon-nitrogen single bond somewhere in this range as well. Again, that's 1,500 and below is our carbon-carbon single bonds and our carbon-nitrogen single bonds. Okay. Now, if we took our amine and converted it to a functional group with a double bond or a triple bond, it's going to change regions, okay? So we're gonna get to this functional group pretty quickly. It's actually next week. These are things with the carbonyl group. The carbonyl group is a C double bond O, and we have aldehydes and ketones, and we also have carboxylic acids. They all share this functionality, and that carbon-oxygen double bond shows up in that 1,500 to 2,000 range right here. Remember, this is just single bonds. This is the carbon-oxygen double bond and carbon-carbon double bond and carbon-nitrogen double bond. So because we have this carbonyl here, we see a nice sharp peak in that range. And we can see that there's no alcohol in this species, no primary or secondary amine, and only carbon-carbon bonds and carbon-hydrogen bonds. But this is the only double bond we have in our system is that carbon-oxygen strong double bond. Okay, taking our carbon, our carbonyl with an OH on it, that turns it into a carboxylic acid group. We have a peak for our OH, which is down here. We have a peak for our carbonyl, which is here. And then we have, of course, our carbon-hydrogen peaks, as well as our carbon-carbon peaks in this range, here and here. Notice again, because we have an OH, we have a big, broad OH peak here, where we would have nice, thinner peaks if they were just carbon-hydrogen bonds. Okay, so notice that there's a slight similarity between the alcohol right here and the carboxylic acid. The big difference between the alcohol is the lack of a carbonyl peak. Okay, so an alcohol will have the big wide peak here, but not the carbonyl peak, where the carboxylic acid will have them both, the carbonyl and the alcohol peak, the OH peak right here. So that's how you can differentiate between your alcohol and your carboxylic acid using IR. Okay, so the last couple peaks I want to talk about are what we call the amide peaks. And if you have hydrogens on your amide, you're going to have as many peaks in that amine region as hydrogens you have, meaning that your primary is going to have 2 peaks in this region. Your primary or your secondary, which is only 1 nitrogen, 1 hydrogen, is going to have a single peak in here. But in this particular case, we have no hydrogens on nitrogen, so we have no peaks in that range. However, we still have a carbonyl, which is here. We have carbon-hydrogen bonds, which are here. And we have carbon-carbon bonds, which are all of these. So we can even tell the difference between different functional groups as we move from place to place to place by looking for those different bonds in the IR spectroscopy. Okay, so here's an example of a secondary amide. Here's where we have a single hydrogen on here. We have our carbonyl showing up in our 2000 to 1500 range. We have our benzene has carbon-carbon double bonds. That's going to show up here. That's our carbon-carbon double bonds. We have carbon-hydrogen bonds here and here. That's these right here. And this peak up here is our nitrogen-hydrogen shift. And again, we have our carbon-carbon bonds here and our nitrogen-carbon single bond here as well. Okay, so, and moving to our last example is our primary amide. Notice again, we have those 2 peaks here. We have our carbon-hydrogen bonds, we have our carbonyl, and then all of our other bonds available to us. There we go. Now, again, our tertiary here had no bonds here. Our secondary had a single hydrogen here, and our primary, which has 2 hydrogens on it, has 2 peaks in there. Okay, so just like amines will have 2 peaks for 2 hydrogens, 1 peak for 1 hydrogen, and no peaks for no hydrogens, the amides show the same, in which you have, if you have 1 hydrogen on your amide, you have 1 peak. If you have 2 hydrogens on your amide, you have 2 peaks. And if you have no hydrogens on your amide, you have no peaks. Okay, so again, if you have to take this entire section of IR down to 1 slide, this is your slide, okay? This is where it tells you the most information. Knowing these wave number zones and knowing the types of bonds in each of these wave number zones will take you a long way at knowing which functional groups, as we learn them, the ones we've already learned and the ones we'll learn in the rest of the semester here, knowing that the different functional groups show up in the different bands is going to tell you everything you need to start with for IR. Okay, questions on IR spectroscopy as it relates to the types of bonds and the functional groups that are associated with those types of bonds. I glitched out 30 minutes ago, didn't I?
No. I don't really have any questions. Are you going to be posting this one today?
I'm going to try. The other one has finished translating, and so it'll be posted here pretty quick. This one takes about 5 minutes to translate, and then it'll be uploaded about 5 minutes later.
Okay.
So yes.
Yeah, because
And they're uploaded to tracks? Sorry.
The videos will be uploaded to YouTube. The slides are uploaded to tracks. And the goal slides are uploaded also to Top Hat and Canvas.
Okay. Thank you.
Since we are doing only 3 chapters this week, does that mean next week we're doing 5?
No. We're going to do 4 next week. And then our last week, we have our last chapter, which is chapter 16, which is polymer chemistry plus 2 days of review.
Oh, okay. So the chapter 16 is just going to be on the final.
Yes, we will not
Okay.
be pre-tested on that. So if we go to, because next week we have chapters 12, 13, 14, and 15, which is really cool because they're all carbonyl related, and you'll see the compare and contrast between them. And then the last one is just polymer chemistry, which is I'm going to lightly touch. It's my favorite thing, but it's going to just show up on the final.
Okay, thank you.
Chapter 9 goals slide should be up. I will check that right now. Let's see. Okay, in Top Hat. Top Hat, they are there. Chapter 9, 10, and 11, and 12 are all on Top Hat. The goal slides through chapter 12 are on Canvas. And let me double check the goal slides on goal slides. The PDFs are through chapter 12 on tracks as well. Let me double check the other one. Oops. I'm going to stop sharing. So chapter 9 goal slides. Chapter 9 goal slides. They are on tracks and on Canvas as of right now. 9, 10, 11, and 12. I'm double checking. 9, 10, 11, 12. I see them on both tracks and on Canvas right now. Oh no, chapter 9 PDFs are missing off of Canvas, off of tracks. All right, I will upload those right now. Might glitch me out, but hey. So yes, you are correct. They are not on tracks right now, but they will be very soon. Okay, so that'll be it for now. Let me go ahead and stop recording.